Greetings. This video is for CALC 2, section 11.10, and we're going to talk specifically this time about the Maclaurin series. So we start with this general form that we've notated as the Taylor series, which is given by the summation of n equals 0 to infinity of the nth derivative of a function f evaluated at a divided by n factorial, and then multiply that times the quantity x minus a raised to the n. So let's write out the first few terms of this summation. So when n equals 0, we have the 0th derivative evaluated at a, so we write that as f at a divided by 0 factorial. And then we would have multiply that by x minus a raised to the 0. When we have n equals 1, we have the first derivative evaluated at a divided by 1 factorial, and multiply that by x minus a raised to the first. When n equals 2, we have the second derivative evaluated at a, and we divided by 2 factorial. We multiply that by x minus a raised to the second, and so on and so forth. So if I write this out in each individual term, what I will get is f of x equals to f, the 0th derivative evaluated at a, divided by 0 factorial times x minus a to the 0 plus the first derivative evaluated at a divided by 1 factorial times x minus a to the first plus the second derivative evaluated at a 2 factorial times x minus a to the second plus, and this would go on until we got to the last term, which would be the nth derivative evaluated at a over n factorial times x minus a to the nth. And usually we don't write it this way, we simplify it a little bit. So we would say that 0 factorial by definition is equal to 1, and x minus a raised to the 0 is equal to 1. So that first term would just be f evaluated at a divided by 1 times 1, so just f evaluated at a. Then the second derivative, or the second term, would be the first derivative evaluated at a, and that's being divided by 1 factorial, which is 1. Being divided by 1 factorial, which is 1. And then x minus a raised to the 1, we usually don't write that part, so just x minus a. And then plus the second derivative evaluated at a divided by 2 factorial times x minus a squared. And the next one would be the third derivative evaluated at a times 3 factorial times x minus a cubed. And then that would go on until we got to the nth derivative evaluated at a divided by n factorial times x minus a to the nth. Let's take a look at a special case. If a equaled 0, then we have the situation of x minus a, take its absolute value as less than r, is now x minus 0, take its absolute value as less than r. So that is the absolute value of x is less than r. In this special case, I'm going to have f of x is equal to the summation of n equals 0 to infinity of f, take this nth derivative and evaluate it at a, but in this case a is equal to 0, and divide that by n factorial, and then multiply that times x minus a, but a is equal to 0, raised to the n. And so that simplifies to the summation as n equals 0 to infinity of f, take the nth derivative, evaluate it at 0, over n factorial times x raised to the n. And this particular case has a special name, and that is the Maclaurin series, named after the mathematician Maclaurin. So the Maclaurin series is a special case of the Taylor series. And when we write out the Maclaurin series, we have f of x equals summation n equals 0 to infinity, evaluated at 0 over n factorial times x to the n. That's equal to plus the first derivative evaluated at 0 times x plus the second derivative evaluated at 0 divided by 2 factorial times x squared plus the third derivative evaluated at 0 divided by 3 factorial times x cubed, and that goes on until the nth derivative evaluated at 0 divided by n factorial times x to the n. So the Maclaurin series has many important applications, the most famous of which is for Euler's number E. So let's look at this example. Find the Maclaurin series for f of x equals e to the x. So we usually make this chart. F of x equals e to the x. The first derivative is equal to e to the x, and the second derivative is equal to e to the x. And if we kept going, we'd end up with the nth derivative is equal to e to the x. So if we evaluate these all at 0, we get e to the 0th, and so that's 1. And then f, take the first derivative, would be e to the 0, and that's 1. And the second derivative evaluated at 0 is e to the 0, so that's 1. And so we go all the way down to the nth derivative evaluated at 0 is e to the 0, and that's 1. So we then have this Taylor series. So when I write out the Maclaurin series, I have f of x equals e to the x, and that's equal to the summation of n equals 0 to infinity of the nth derivative evaluated at 0 over n factorial times x to the n, and that's equal to, so that would be equal to f evaluated at 0 divided by 0 factorial times x to the 0 plus f, take the first derivative evaluated at 0 over 1 factorial times x to the first plus f, take the second derivative evaluated at 0 over 2 factorial times x squared. And we'll go on forever until we get to f, the nth derivative evaluated at 0 over n factorial times x to the n. And the first coefficient is equal to 1 times x to the 0. The second coefficient is equal to 1, times x to the first. The third coefficient is equal to 1 divided by 2 factorial times x squared, 1 over 3 factorial times x to the third. The next one will be 1 over 4 factorial times x to the fourth, and that's going to keep going forever until we get to 1 over n factorial times x to the n. And so when I write that out, I have f of x is equal to e to the x, and that's equal to the summation of n equals 0 to infinity. And this f's take the nth derivative and apply 0 will always be a 1. This is a 1, and so that'll always be a 1 divided by n factorial times x to the n. And traditionally, we write that out as the summation of n equals 0 to infinity of x to the n divided by n factorial. And so now what we say is we have e to the x is equal to the summation of n equals 0 to infinity of x to the n over n factorial is the Maclaurin series definition of e to the x.